Hello and welcome to the third video of the Basics of Audio Technology training series. Again, if you have not watched the introductory video, please stop and go watch that now so that you understand what this video series is all about and so that you can get a copy of the companion book. But without further ado, we're moving on to analog and digital electrical audio. Now, the world of electricity and the physics and math behind it is huge, vast, and complex, and I'm only just going to barely scratch the surface of it just to give you an understanding, an idea of how electrical audio works within cables and speakers and microphones. So in order to transport audio via electricity, we have to complete a circuit. And a circuit is just a path for electrical current to flow. And in order for that to flow in a circuit, it needs to be a path that is also a loop. So you might be thinking, if I plug in a microphone cable here and here, that's just point A to B. So how is that a loop? That's just a straight line. Well, within cables, we will have two conductors. And those conductors, when connected to the device or instruments on the end, will create a circuit. They will create a loop. The other things that we need for a circuit are current, voltage, and resistance. The current is just the flow of electric charge within the circuit, and that is measured in amps. And voltage is the potential force, or the force that allows the current to flow, and that is measured in volts. And the resistance, because everything has friction, as the electrons travel through this copper wire, there will be friction. That inherited opposition to the flow is called resistance, and that's due to friction, and that is measured in ohms. Now, there's two different types of electrical circuits or electrical currents. The first is DC, and the next is AC. DC is direct current, and AC is alternating current. And the difference between them is the current only flows in one direction. It will only ever have a positive voltage value. Whereas the current can flow in alternating directions, and the voltage can have positive and negative values. When it comes to analog electrical audio, in order to transmit a signal, we need to be using AC currents, so that we have a positive and negative value. And I'm just going to show you here, just as an example. We'll talk about this figure later. But an AC current moves in both directions. It moves in positive and negative. DC only will ever move in a positive fashion. So when it comes to electrical audio, the frequency of the voltage change directly correlates to the frequency of the sound pressure wave. And the amplitude of the voltage change, positive and negative values, how far away from the center, directly correlates to the amplitude of the sound pressure wave. So when we're talking about a microphone, like we learned in last chapter, when the diaphragm, say in a dynamic microphone, when a diaphragm is moved by sound pressure waves, that is going to move the coil of wire around the magnet and induce a voltage. How quickly that diaphragm moves back and forth due to the sound pressure wave determines how quickly the voltage will change up and down. So we have a one-to-one correlation of frequency from sound pressure to electricity. And how far the diaphragm moves based on the amount of energy from the sound pressure wave directly correlates to how far from equilibrium the sound pressure, the wave will move in electricity. So again, we have a one-to-one representation of sound via electricity in an AC current. But we also need to know, where exactly is this zero? If we just have a changing sound wave, we can just blindly choose, like, this is zero and these are the positive and negative values. But that's not how it works in a circuit. We will have a ground or a zero voltage reference, and that's where those two conductors come in. So if we have our cable, we have two conductors. One of the conductors will be a positive or hot, and you're probably familiar with positive, negative, and ground connectors maybe. So the positive is where the voltage is going to transfer from its source, or be delivered from its source to its destination. And the ground wire is the where the current will return at a zero or near zero voltage for reference. So that way we can accurately know when we have this changing voltage that the reference of zero is not here, but actually where it needs to be. Now, the reason the ground cable is called the ground is because in electrical circuits, there is literally a ground. So in your house or the building or church, wherever you're working, somewhere you're going to have a circuit breaker box where all of the outlets and everything in your building are going to be going to one breaker box. And that's where, when you probably turn on your space heater, and your hair dryer, and all of a sudden you blow a circuit. And so you have to go and flip it, the breaker box, and get your power going again. Now that circuit breaker box is literally connected via a copper wire all the way to a copper rod in the ground. So that way your entire house is grounded and you have that zero voltage reference. And it's also a safety mechanism when it comes to electricity, which we'll talk about more later. But that is just the very basics of how analog electrical audio works. You have to complete a circuit, you have to have a loop, you have to have current. That's the flow of electrons going, and you have to have voltage. Without the potential for a current, with no force pushing it, nothing's going to move. So you have to have voltage, and then there is resistance within a cable. In AC circuits, the resistance is called impedance, and we will also talk about that more in just a second. But that is the basics of electrical analog audio. There's a circuit, we have a one-to-one representation via voltage change for a sound pressure wave that is going through a minimum of two conductors. Next, we're going to talk about common problems within cables, or we can say more accurately, within circuits of analog audio. So common problems within an analog electrical audio circuit. And remember, a cable is physically part of that analog audio circuit. So we have to take into account the nature of the cables we're using. So really, I can rephrase this to common problems within cables of analog electrical audio circuits. And the first problem we'll talk about is an RC low pass filter. So remember, as electrons are flowing through the cable, there is an inherited resistance due to friction. And that resistance can be made worse by two things. The first is the thickness of the cable. The thinner the cable, the more resistance you'll have, because you have a lot of electrons trying to flow through a very small space. The thicker the cable, the less resistance you'll have. The second issue is the material that you're using as the conductor. So copper is a very good conductor of electricity. However, copper is also very expensive. So manufacturers will usually blend different metals to form a copper alloy, which they make their wires with. But that reduces the amount of conductivity, which means there's going to be more friction, so more resistance. The next part of the RC low pass filter is capacitance, or a capacitor. Now, we talked about a capacitor in chapter 2 with condenser microphones, and simply a capacitor is something that holds a static electric charge. And within the microphone example, there was two plates that held a static charge in between them. But we don't have plates here. We have two conductive wires. But still, between the two, they can hold a static charge when this is a circuit and we have voltage flowing through. And what will make capacitance worse in a cable is the length of the cable. The more surface area you have between the two conductive wires, the greater static charge or capacitance that you can have between the two cables. Now, when you add a resistor and a capacitor to an AC circuit, you will create an RC low pass filter. Now, when it comes to audio, that means that low frequencies will be let through, and high frequencies will slowly be cut off. Now, there's a great example I found on YouTube that I've linked in the description. It will give you a very good demonstration of hearing the RC low pass filter. He uses his bright sounding guitar, puts it through a very, very long cable to get the RC low pass filter, and you can hear how it changes the tone. It literally cuts off the high frequencies in the signal. So I'll stop now and give you a chance to go watch that video. Okay, so hopefully you stopped and watched that video. If you did not, I'll give you one more chance. Go and watch that video. After watching, you should have a really good idea of an RC low pass filter and how it does change the frequency response of the signal, of the original signal. Now, in that video, you probably also noticed he was talking a lot and using the word impedance, and that's what we're going to talk about now. So, impedance is the complex form of resistance for the entire circuit. So far, we've only been talking about resistance as the inherited resistance within the cable due to friction, but there's an also complex form of incorporating all factors, and that will give you the total opposition to flow, the total resistance of the entire circuit, and that is known as impedance. And you've probably more seen it as low Z or high Z because there are two different types of impedance, low impedance and high impedance. And again, on devices, DI boxes, microphones, you probably see it as low Z or high Z, and that is referring directly to the impedance. So high impedance means that there's great resistance, which means that there is a low current flow. Low impedance means that there's less total resistance, means that there's a higher current flow. And so to try to give you a picture and wrap your mind around this, let's think about hoses, water hoses. Think about a garden spigot and a garden hose and a fire hydrant and a fire hose. So high impedance signals, they have low flow, which means they're going to need the right cable for it to transmit that. So you put the high impedance garden spigot to a garden hose because it's going to have low flow. You can only turn it up but so much. You only have so much water pressure. And to get your water from point A to point B, you need a thinner garden hose to allow it to go. Now, the same for the fire hydrant. It has a large amount of current, so you have to put the right hose to get the job done. If you try to put a garden hose on the fire hydrant, the hose is going to blow off or rip apart because there's too much going through it. So you really need the fire hose. And then vice versa. You can't get the water going all the way through a fire hose when it's connected to a garden spigot. And so that just very simply kind of demonstrates the issue when you have impedance mismatch problems. You need to make sure that whatever device you're using, you understand whether it's a high impedance or low impedance signal, and the device you're trying to connect it to, whether it accepts high impedance or low impedance signals, because you're going to run into issues of not having enough volume, having too much volume over time with too much voltage on a thin gauge cable, kind of like the fire hydrant and a garden hose. You could create fires. So this is a very real issue. But in short, just understand what you're working with, recognize whether it's high impedance or low impedance, and make sure that they're connected properly. But for the most part, you don't really have to worry about that because microphones put out low impedance. Just about everything is kind of universally plug and play. But there are some very important problems that you do need to pay attention to when it comes to impedance. And the first comes with high impedance signals. Remember, high impedance means more resistance, meaning a low flow. So if you want to send a high impedance signal over a great distance, you're going to run into problems. And again, we have that nice RC low pass filter. Again, you cannot simply connect an electric guitar on one end of the room and then 100 feet away try to plug it into a console, because you're going to severely degrade the audio quality via the low pass RC filter, because high impedance signals have more resistance. They're going to be more susceptible to the RC low pass filter. At the same time, with the added capacitance of a longer high impedance signal and more resistance, you are essentially just creating a really big antenna with a high impedance signal. So if you're trying to go a great length with a high impedance signal, you're just making a really good antenna and just asking to pick up radio frequencies in your system. And I've experienced this before with very poorly shielded guitars and very powerful amps, and all of a sudden the bass player moves in one direction and the radio starts playing through his amp. So it's a very real problem. So what do we do if we want to get a high impedance signal a great distance? Well, you just convert it to a low impedance signal, and we do that using what's called a DI box, which stands for direct injection, or a direct box, or there's probably other names that you've heard, but more often it's a direct or DI box. And that simply will just change it and convert it from a high impedance signal to a low impedance signal, so that you can get your guitar signal from the stage all the way to the back of the room, and you won't have issues of the high impedance issues. Because again, high impedance means more resistance, and again, low impedance means less resistance. So because it has less resistance, it's able to travel a greater distance. The next is you also want to make sure that when you are using high impedance and low impedance signals, you just want to make sure you're using the right cable for it. If you're using a high impedance signal, you don't want to be using these super thick speaker gauge wires, because again, you have low flow and you have really thick wire meant for high flow, high voltages and such. You're just going to run into issues of not being able to power what you need. So make sure you're using cables that are labeled instrument cables, when you're plugging in a high impedance signal, and then vice versa. When you're plugging into speakers, just make sure that you have speakers that are low gauge, high, and just labeled speaker cables. Just know what you're working with. And again, with the microphones and everything I'm going to talk about, just stop and read the manual. Get an idea for what you're working with, and that's going to save you so much heartache. And so those are the problems with high and low impedance. You want to make sure that the impedances match, and then when you're using high impedances, make sure that you use shorter cable lengths. For high impedance, they say no more than 25. Some people say no more than 20 feet of length. And if you do need to go above that, you switch over to low impedance signals. And then lastly, make sure that you're using the right cable for the job. And so those are the issues with impedance. Next, we're going to move on to interference. So interference, we have two main types of interference. The first is EMI, electromagnetic interference, and the second is RFI, radio frequency interference. Now, EMI, again, electromagnetic interference, is broadband, meaning it's over a large range of frequencies. These are most typically introduced from power transformers, dimmers, fluorescent lights, other audio devices, or just power cables. The number one way to avoid EMI into your system is to avoid putting your audio cables, so here we have a microphone cable, and let's call this a power cable, just having them not together, just physically distancing your cables away from each other. So I'll give you two scenarios. You have a power cable running down the side of a wall, and you have to run an audio cable down the same wall. So what do? Simply just move them apart. Even moving them apart by 1 inch, having them run down the wall, can drastically reduce the amount of EMI introduced into your system. And the second example, let's say on your computer desk or on the stage or something like that, we have different things plugged into different sources. You're going to have power cables run into audio cables at some point. It's not 100% unavoidable. But what you can do is reduce the amount of layover between the two cables. The more surface area that you have between the two cables, the more EMI that's going to be introduced into your cable. And so rather than having it cross over and kind of a lazy X pattern, have it cross over as perpendicularly as possible so that you minimize the contact point to have as least surface area as possible to minimize the EMI. Now, the next type of interference is RFI, radio frequency interference, and that is narrow-banded interference. This is typically cell phones, computers, Wi-Fi, most electronic devices, and also remember, via impedance. High impedance signals over longer spans can act more like antennas. Secondly to that, when we wrap high impedance signals, or even sometimes low impedance like microphones, if you wrap them around very metallic microphone stands or other stands, you wrap them too many times, well, you're creating another antenna as well. So only wrap once or twice to keep the microphone wires up and out of the way, or whatever cables you're using, or better yet, maybe even just use a clip. So a way to the first way to reduce RFI is to reduce the antenna-like characters of the cables you're using. Shorter spans of high impedance signals and less wrapping around your microphone stands. Now, the second all right, so this is where the audio of my recording corrupted. You could start to hear it happening at the end of that last clip. Basically, what I'm going to say is the second thing that you can do to reduce RFI is to not put cables next to things that emit radio frequency signals. So, for instance, don't put a cell phone on cables. Don't put your cell phone in the same pocket as a wireless microphone pack. Don't put computers next to things. Don't put your wireless microphone packs next to the cables or on top of cables. Basically, just don't put cables next to things that emit wireless signals. That's the second thing to reduce RFI. And the last thing is just have properly shielded cables. And so we're going to stop and go into an example here of the different types of cable shielding, just to give you an idea of what they are, the pros and cons to them. And then after that, we're going to move into the last thing to help reduce interference, which is balanced signal methods. Okay, now I'm going over the 3 different types of cable shielding as seen on page 38 and 39 of the book. The first type of shielding is called a serve, and that's simply when 2 conductors are wound helically around each other. This doesn't actually help against any radio frequency or electromagnetic interference. It's simply just a way to reduce capacitance between the 2 conductors, which will help against RC low-pass filters and for high impedance signals also kind of turning into an antenna. The next is a braid. That's simply when you have a conductor like this one here that's just surrounded in a copper braid. This one's actually not braided, it's just spiraled in the copper wiring, but sometimes they actually do braid the copper wiring like a tube and put the conductor within it. The next is a foil, and foil is simply just foil around the cable. Foil is more effective at radio frequency interference rejection, and a braid is better at electromagnetic interference rejection. Now I'm going to go over these cables and just explain just a little bit about them and the pros and cons of each. So this cable was the cheapest. It only came in a serve and a very loose one at that. I kind of had to twist it even more. So it had no shielding whatsoever, and this is a speaker cable. So it's actually going to be very poor at rejecting electromagnetic and radio frequency interference. It's the cheapest speaker cable that you could probably find out there. The next is another speaker cable with a lower gauge, so just a smaller conductor. I guess technically it's a higher gauge, and all it has is just a foil shield around both of the conductors together. So the conductors themselves aren't isolated from each other, but that's going to have good radio frequency interference, which for a speaker cable at high voltages is going to be good because it's going to act more like an antenna. And the next here is the braid. I'll go with this one here. This one also has foil around the outside of the entire cable, but then it also has foil inside each conductive sleeve, but not in between each smaller conductor. And so this one's a little different because it's a snake. It has 8 microphone cables or cables within it, and in each one there's 2 conductors for each. Well, 3 technically. One's not shielded with rubber. And so the reason they decided not to go with a braid shield is because it would be too bulky, and the point of a snake is to reduce the amount of size. So if you can imagine 8 of these is in here. So greatly reduces size, but they can't do braid shielding, so they just sacrifice that with foil. And foil is one of the cons to foil is its durability is low. So just like with a paper clip, if you bend it back and forth a lot, eventually it's going to break. The same thing with a foil, and then its effectiveness in shielding goes down, and so it's not as flexible. A braid doesn't have that problem, but it takes up much more room. So braid, you can bend back and forth, has a lot more flexibility, but it's not good against radio frequency interference, just against electromagnetic interference. So this cable had 2 conductors, both were wound with their own separate braid, which means they're isolated from each other from crosstalk, and from the outside from electromagnetic interference. But this is a microphone cable, so it needs to be a balanced signal, so it needs to have 3 conductors. So this one only has 2 built in, and you have to use one of the braids as the ground conductor, which is not the best. So this one's a little cheaper because it doesn't have a dedicated one. Like this next one has 3 dedicated conductors, but only 1 copper shielding around the entire thing. As you can see, let me focus this at right there. It's around the whole thing, and I just peeled it off here. So they're not isolated from each other like the last one was, but they have 3 dedicated conductors, which makes it a little better for balanced signals or stereo signals. Now, the absolute best shielding would be have braided shielding around each conductor, foil shielding around each conductor, and then they would be very, very well insulated from radio frequency and electromagnetic interference. However, when you do that, you're going to end up with a really, really thick cable, and it's not going to be very flexible like this microphone cable is, and its durability is going to go down considerably. So you have to weigh the pros and cons of each, and I think these 2 microphone cables are good examples. This is a fairly good microphone cable, just one singular braid. You can add a foil around it. It'll increase the cost because of material, but it's pretty good. But the moral of the story when it comes to cables is just don't skimp out on cables. You don't want to buy the cheapest of the cheap that has absolutely no shielding like this one here. It's just not going to be worth it. You're going to run into too many problems. Another thing with these cables, you may be wondering, why don't the microphone cables have the foil shielding? Well, microphone cables typically are going to run low impedance signals, which means they're going to be less susceptible to that turning into an antenna effect due to capacitance, because they're going to have low impedance signals. So foil is not super necessary because it's not really going to be much of an antenna. However, electromagnetic interference is much more important because if you're running this across the stage, you're going to intersect and come across different cables, maybe holding different power supplies. So like if you're powering a piano or a keyboard or something, that microphone cable or instrument cable is going to come up really close to those power supplies, and you're going to have a lot of electromagnetic interference. So braided shielding is better for that purpose. So again, these are the different types of shielding, kind of some pros and cons to each, but the moral of the story is don't get cheap cables. Go for about a middle of the road, or if you have the money, you can buy a really expensive one. Balanced signal methods happen via electromagnetic induction in a transformer. And as we learned in Chapter 2, talking about dynamic microphones, when you have a coil of conductive wire suspended in a magnetic field, any changes to that magnetic field will induce a voltage change in the coil of wire. Now, transformers work under that same principle, just in reverse. So turning to page 40 of the book, here you see a diagram of a very simple transformer. We have a magnetic core, which creates the transformer core, and on either side, we have 2 coils of wire. Now, in a transformer, we are not changing the magnetic field and inducing voltage change in the wire. Instead, we are inputting a current to induce a voltage change on the other one. So our input is going to be transformed through the core into a different output system. And what determines the change is the coil. How many turns are in the coil and which direction the coil is going in. So in this diagram, we have 12 turns on this side and 6 turns on this side. The coils are going in one direction here and in the opposite direction on the other side, which means our input signal is going to be halved and then out of phase out on the output signal. It is going to be transformed. So we can turn to the next figure to get a better idea of this. Here we have just a simple representation of a transformer. 4 turns on the input, 4 turns on the output, and the coils are going in the same direction. So our input signal is going to be the same as the output signal. In the next, we have 4 turns on the input, 2 on the output, and they're both in the same direction. So our input signal, the amplitude is going to get halved, but it will still be in phase because the coils are going in the same direction. In the next one, we have 2 input coils and then 4 output coils, and they are in opposite directions. So our input signal amplitude will be doubled and also be 180 degrees out of phase. Now, we already talked about phase in chapter 1, so this should not be new to you. And this transformer principle of electromagnetic induction is what creates balanced signal methods, as we'll show here on the next page in figure 18. We have our original unbalanced signal that's going to go through a transformer. And on the other end, we have 2 separate coils of wire, and these coils are going in opposite directions from each other. So we will have 2 signals being outputted, both half the original amplitude, one of which will be in phase and the other will be out of phase. So I'm going to stop here and point out that in order to first have a balanced signal method of audio being transported, you need a minimum of 3 conductors. So remember, for an electrical audio system, you need a minimum of 2 for your positive and ground. But in order to have a balanced signal method, a balanced signal going through, you have to have 3 conductors. One will be for your positive, one will be for your negative, which is the half amplitude out of phase. Your positive is half amplitude in phase. And of course, you still have your ground 0 reference conductor. So that's very important to remember, and we'll talk about that in a little bit when we talk about different cable connections. But for now, we have our balanced signal. It's going through our cable via the 3 conductors. Then we have interference being introduced. This interference is going to be introduced in phase with itself on both sides. Now, when our signal reaches its source, there's another transformer. That transformer has 2 sets of coils on the input, both out of phase from each other, and then will be summed up together in the output. And so what happens is you have your in-phase signal with interference here, your out-of-phase signal with interference here, which then gets flipped in phase with these 2. And we know, due to phasing, what we learned in chapter 1, the positive values of the interference here are going to cancel out with the negative values of the interference here, so that you're left with your original signal with the interference being canceled out. And so that is a balanced signal method. Now you're probably wondering, how do you do this? What does this? And the first one is the DI box. We've already talked about a DI box, the direct box. Not only does it match impedance, but it will also turn it to a balanced signal. Not all DI boxes will, but for the most part, they will. And how do you tell whether or not a device or instrument outputs a balanced or unbalanced signal? And that's simply, it'll say on it. It'll say balanced or unbalanced, or for short, just BAL, BAL or unbal. Now, sometimes the markings rub off, or not all manufacturers print it on there, so then what? Then you just go look at the manual, and again, it's all about learning what device you have and understanding it so you know. And so you can't connect an unbalanced guitar signal into a balanced connection and expect that you will have this phase cancellation of interference. You have to have a balanced signal from the source and being summed up together at the end. And again, just look for the labeling on that. Now, one thing that a balanced signal will not guard against when it comes to interference, balanced signals will help against EMI and RFI, but it won't help with ground loops. And so we'll talk about ground loops now. Remember that we have to have the ground connector in our signal. So now we're talking about a balanced signal. We have our positive, our negative, and our ground. That gives us our 0 reference voltage. But every device that we have, as we talked about earlier, when you plug it into a wall, it's going to be connected to your breaker box, which is connected to a physical ground, or some things may not be grounded. And from one device to another device, you're connecting to the two. You may have different ground levels. This might be 0.05 and this might be 0.01. Your ground is not completely the same. And so that's going to cause what's called a ground loop, which in America, with our electronic system that we have, is going to be a 60 hertz hum that you're going to get. In other countries with different protocols for electricity, that'll be a different frequency, but in America, that is a 60 hertz hum. And so if you hear a 60 hertz hum, it's either that you're really close to another sound source and you're just getting EMI, or it's most likely a ground loop. So how do you fix the ground loop? Well, you can use a DI, or there's other buttons on different devices, but essentially you just disconnect the ground from one device to the other, not necessarily disconnecting the ground within the cable itself. Now, disconnecting the ground from one device to another through the so that we get rid of the ground loop is a very easy thing. Most DI boxes have a lift switch on it, and it's a ground lift switch. And essentially, you can choose to connect the ground between the two systems or lift the ground so you do not have the ground loop problem. But there's one thing that you should never ever do in order to lift the ground. Let's say you're connecting from one device to a cable to another device, but neither anywhere in the cable do you have a ground lift switch, or in any of the devices do you have a ground lift switch, so that you're stuck with a ground loop. Now, I've seen people take the electric plug of one of the devices, pull it out of the wall, and then pull out the third ground pin and then plug it out on the wall. That did fix their ground loop problem, but instead it created another problem that is much more problemsome. and I do not recommend doing it at all. What they did is they disconnected the ground from the ground through the electric circuit in their house and their building, so that if a problem does arise, rather than the excess voltage being dissipated and sent to the ground as a safety measure, there is no grounding. That can result in fire or people being shocked. And there are accounts of people being electrocuted and fires happening due to no ground on some devices. So if you do run into a ground loop problem, do everything that you can to find a device that will safely disconnect the grounds between the two devices, but never pull the ground out of a plug that goes into a wall. That is a big hazard. And so that is everything you need to know about a balanced signal method. It uses transformers via electromagnetic induction. It takes that signal, splits it in two, one phase, half in phase, one out of phase half, and then as it's summed together on the other end, all of that induced interference will be phase canceled out, but it doesn't fix the ground loops. So again, to fix the ground loop issue, you just simply lift the ground so that it's not connected between the two devices. And again, you do that with either a built-in button on either device, a DI box, but never do it by disconnecting the ground of the power outlet or the power cable to the outlet. And so now we're going to move on to our next section, which is types of electrical audio connections. And this is where we can start to talk about the differences between conductors. And I made a video that goes through the different types of connections. But again, just to reiterate before we go into that, for a balanced line signal method, balanced line signal, you have to have 3 conductors. And without taking a cable and breaking it open and physically looking in within them, how do you know whether or not it has more than 2 conductors? And most cables you can tell by looking at the ends of them. So we'll go down this list here and I'll just show you briefly. For a 1/4 inch plug, this is unbalanced because there's one conductor, a second conductor with an isolated ring in the middle. So this is called a tip sleeve, and that's an isolator in the middle. So this has 2 conductors. Now we have the same exact form here, but we know that there's 3 conductors. 1, 2, 3 because there's two isolating rings between them. So there's a tip ring sleeve. Now XLR cables, if you just look on the side, we have 1, 2, 3 plugs. So this has 3 conductors. Banana plug is really easy. 1, 2, just 2 conductors. RCA plug, it's a little harder, but we know that it just has the outer sleeve connection and the inner. It is just a 2-conductor connection. And the Neutrik Speakon connection is a little harder. We can't look on the inside here. We can't look there. You physically have to know which connection you have. There's different types of Speakon connections, and so you can have balance or unbalanced, but for the most part, these are typically unbalanced. And then a spade plug is really simple. One connection. This is just one simple, this is one simple connection, so you have 2 conductors in the cable. And so now I'm going to go to the video of different types of cable connections. There we go. Okay, now I'm going to be going over the most common types of connectors that you're going to see as a just normal average Joe volunteer or just somebody in a band. This is not an exhaustive list. There's a lot of other connectors that you'll see in more professional settings, bigger settings, but these are the ones you're going to see day in and day out. I'm just going to start first here on the left with an XLR connection, also known as a microphone cable. Why it's called a microphone cable? Because 98% of microphones use this connection. There are other types of microphone connectors, but this is pretty much it. Now, these don't only plug in microphones, they also plug in other devices as well, so they use for a lot of different things. This one here is a female connection, and this one is a male connection. Also note on the XLR, they do have 3 conductors on the inside, so they can hold 2 channels of audio, or they can hold a balance signal. The next is a 1/4 inch connection. It's called 1/4 inch because it is a 1/4 inch wide. You can see smaller ones that go to headphones. Those are 1/8 inch connectors as well, but they're the exact same type, just a little smaller. I have another one here because there's a difference between the two. The top one is a tip sleeve connector, also just having 2 conductors, so it can be mono signal and non-balanced, where the bottom one is tip ring sleeve, so it can have 2 channels of audio or be a balanced signal. So again, tip ring sleeve with 2 isolators, tip sleeve with 1 isolator. And then here we have a female 1/4 inch connection. On the end of this cable, we have a dual banana plug. This would be used for the back of an amp to go to a speaker. And so this cable converts it from a banana plug into a 1/4 inch connector. The next, you'll probably have seen these on the back of your TVs at home. You'll most often see them on audio interface devices to go from like a computer to your system or something like that, or for some smaller speakers as well. This is an RCA plug, also known as a phono plug. You've probably most seen them with the nice red, yellow, white connection, or the old school HD red, blue, and green connection. There's absolutely no difference on the inside of those cables. The only reason they're colored differently is just color coordination, so you don't plug in wrong signals to the wrong jacks. But on the inside, they're all the same. The next connection is a speak-on connection. I only have a male connector here, but there's a female out there. You can see that on page 43 of the book. Now, these are typically used for speaker connectors, but high-powered speakers. They're a much thicker gauge, much more secure connection, so there's less chance of somebody pulling it out or something like that. These cables last a really long time. You'll see these most in professional settings or with really high-powered speakers. The last one that you might see if you're working with digital audio, all these cables so far have been analog audio cables, is a Toslink or optical digital audio cable. And that literally is an optical cable, so it shoots light through the cable. This one's nice and cool because it's clear, so it glows when it shoots the red light through it. And it sends a digital audio signal. Another digital audio cable that you might see, but probably not, is going to look like a funky 1/4-inch cable, except it's got a rounded top to it and not kind of a point. If you see something like that, don't try and stick it into a 1/4-inch jack because it is a digital cable. It's also a bantam connector is what that's called. Again, this is not an exhaustive list. These are just the examples that you'll most likely see out there. So hopefully you've seen a lot of those different cable connectors, and now you have a better understanding of the different types that there are and what they're used for. But now you can easily identify which cables can be used, can or cannot be used for stereo or balanced signals. But now we're going to move on to digital electrical audio, the last part of this chapter. We're not going to spend nearly as much time as we did with analog audio, but it's just the same. This world is very complex and vast, and there's so much to it, and we're only just really going to scratch the surface of it to give you an idea of what's happening in digital electrical audio. So when we do talk about digital electrical audio, we are talking about the world of computers, and we're talking about code, a language that they are talking, and all code on computers is based on the binary number system. So if you turn to page 44 of the book, you can see a table here representing the binary number system, also known as a base 2 number system. Our number system is base 10, and you're probably all well familiar with that. So I don't need to teach you about that. I'll just go over binary. So each space, each bit, it represents a certain value, and that value can either be turned on or off. So this bit here represents 1, 2, and 4. And we're capped here at a bit depth of 3. We can only have 3 different values that we can represent, either turned on or off. If we increase the bit depth, also known as the word length, we can have more integer values. So it'd be 1, 2, 4, 8, 16, 32, 64, 128, 512, so on and so forth, doubled all the way up. Now, when it comes to audio, most common bit depths are 16 bits, 24 bits, and 32 bits. So this is just 3. Can you imagine how high of a number we could represent if we had 32 of these and they were doubled all the way up? That's a huge number. So a lot of different integers and different numbers that you can represent. And when we're talking about audio, digital audio, we're just taking data points, and how the more data points that we can have, the more accurately that we can represent analog audio. So again, common bit depths are 16, 24, and 32 bits. Now how binary works is simple. These are either on or off. The 1 position is on, so it's 1. 2 position is on, it's 2. 4 position is on, it's 4. All 3 positions are on, 1 plus 2 plus 4 equals 7. And so that's how binary works. Again, the greater the bit depth, the more data values that you can have that you can more accurately represent analog audio. But the next thing is sampling. We have to know how many samples of audio should we take for those data points to also accurately represent it. And that'll move us over to the Nyquist theorem, which simply just states that if we want to record a frequency of 20,000 kilohertz, then we need to take a sample rate of at least 40,000 kilohertz. So if we want to record 20K kilohertz, then we need a sample at 40 kilohertz. And if we don't do that, then we're not going to be able to capture those frequencies. As you can see here on this table, this is proper sampling. Take a sample here, and a sample here, and a sample here. We can get that frequency. If we're not sampling enough, double the interval as this one, we're going to miss this data point, and our data is going to inaccurately represent as there wasn't sound there. There was nothing there. So those higher frequencies are going to get cut off. Common sampling rates are 44.1 kilohertz, 48 kilohertz, 88.2 kilohertz, and 96 kilohertz. All right, so now we have 2 things. We have number values, which can represent data, and we know how often we have to take them. But what do they affect when it comes to sound? So sampling rate, if we don't have enough samples, obviously we cut out frequencies. We don't collect enough sound. Specifically, we're not going to get the higher frequencies. So the higher the sampling rate, the more accurate we can get our waves, our sound waves to be represented, but then we can also get higher frequencies represented as well. And then when it comes to bit depth, the higher the bit depth, the better dynamic range or amplitude that we can represent. So on this table, or this figure here, you can see if we only have a bit depth of 2, our dynamic range is either up or down. There's loud or quiet. As we increase our bit depth, we can have more quantization intervals, which means we can have a larger dynamic range. We can have really loud, not so loud, a little bit loud, normal sounding, quiet, and then all the way back down to nothing. We have a larger dynamic range. So the bit depth specifically correlates to the dynamic representation of the wave, and sampling is how accurate are we and if we're getting those high frequencies. So if you're recording something that has a vast dynamic range, such as an orchestra, and you have one microphone, you're trying to capture the entire thing, orchestras can be very, very loud and they can be very, very quiet. So you want to record at the highest bit depth to have accurate dynamic range representation. Now, when it comes to sampling, 44.1 is enough, because if you're just recording something for human ears, our upper limits are 20,000 kilohertz or 20 kilohertz. Recording at 44.1 kilohertz, you're going to get those high frequencies, but you might miss a little bit here, but it's perfectly fine. So if you want the best of the best, you get 32 bits at 96 kilohertz. But you're going to take up a lot of hard drive space, because remember, more bits, more samples equals more data equals more hard drive space. Luckily nowadays, hard drives are becoming cheaper, so if you want to record at the highest bit depth, at the highest sampling rate, go ahead. But if you need to save on hard drive space, 16-bit, 44.1K is going to work for almost every scenario. You don't have to go for the highest settings. Another thing to note is you need to understand where your finished product is going to. So if you're trying to upload online, or you're trying to keep file size down, or you don't have a lot of space, or you're trying to whatever it is, just keep in mind more bit depth, more sampling rate, higher the file size. And so if you're streaming audio, you want to keep it to a lower bit depth and a lower sampling rate, so you're not taking up a whole lot of bandwidth, so that your stream is going a little better. And then for CDs, if you're still using CDs and you want to burn some music onto a CD, CDs are capped at 16 bits. And so this is going to lead into our next section, which is word length reduction. And so if you're recording, because you have plenty of hard drive space at that 32-bit 96K settings, you're going to take up a lot of space. But then let's say you just want to quickly upload it online, or have a backup, or share it with a friend, or stream it later, or put it on a CD. You're going to have to reduce the word length. And so we're going to talk about word length reduction next. So word length reduction, as we just said, you can use the highest settings and take up a lot of space on your hard drive, but there are going to be times where you need to have smaller file sizes, or if you're burning audio to a CD, it has to be 16 bits. So you're going to need to reduce the word length. And so that can be done in 3 ways: truncation, dithering, also known as redithering, and noise shaping. In the world of computers and all the tools we have available to us now, you really don't need to worry about truncation. Truncation is when you have, let's say, 32 bits, you want it down to 16, it just cuts half of them off. It rounds all the integers up to the best as possible to try and accurately represent the sound wave. But it introduces a lot of noise and false harmonic distortions. It's just not going to sound great. But again, you don't have to worry about that. The next is dithering or redithering. So what it does is it'll add a low-level white noise to your entire recording, and then randomly kind of truncate those bits off and round them similarly. But with a white noise, it's going to create much less harmonic distortion and try to sound more natural. And when it comes to computer processing power and the amount of, high-end calculations you have to do, dithering is really simple. And it's probably what's happening most in any computer program that you're using nowadays. It's probably a redithering program. And it's very fast and convenient, and it does the job. It's called redithering because dithering occurs in the initial quantization process when you're converting analog audio into digital audio, and so it's called redithering because it's doing the quantization process again, just in the opposite direction. Now, the last one is called noise shaping, and noise shaping is the best, but it also needs the most resource when it comes to a computer. If you're working on a 10-year-old computer with not a lot of RAM, not a lot of hard drive space, and you've got an updated brand new software, and you're using all these highest noise shaping settings, your computer may not handle it. It could crash. And it could be expensive too. There could be some specific hardware devices that you can buy separately that have noise shaping word length reduction processes, and it's just going to be expensive because it requires a high amount of math and precision and calculation. And like dithering, what it does is it adds a noise to your recording, but it's a very specific noise. And then through highly calculated process, it doesn't randomly truncate. It specifically truncates specific values, and it has the least audible distortions of all the three. But again, in the world we're living in today, with the computers available, the programs available, you don't need to worry about what's happening, what type of dithering or noise shaping that you're using. Any of the generic ones will probably suffice for what you're doing. If you want to learn more about this and figure out what's the best, then Google it. I will also put a link in the description to a video below that goes more in depth about digital electrical audio and the different types of dithering and noise shaping and truncation and stuff like that. There's a lot of resources such as Wikipedia that go into all of these at length. But again, I just want to cover it so you understand and just say that whatever you're using on a computer is typically fine. Now, I'm going to take that and then add a stipulation to it, and that's the different file types. So there's MP3s, MP4s, like there's all different types of different audio files. Sorry, MP4 is video. So MP3, then there's AAC, and all these different types of audio files, and you might be thinking, well, which one is the best? Which one is not going to affect my music the best? Well, all of them use some sort of dithering noise shaping process when you convert it down to it, and they do it in slightly different processes, but for the most part, anything other than an MP3 should be fine. MP3 is the worst. It's the most common, or was the most common. It can add some more false harmonic distortions and a lot of kind of noisy, staticky stuff. If you're really listening in high quality headphones or speakers, you're going to notice the difference between an MP3 and a FLAC recording. But again, the difference in the two is file sizes. If you have an MP3 at a certain sampling rate, it's going to be a smaller file size as opposed to a FLAC or an AAC at a higher sampling rate. So it's all a system of checks and balances, just pros and cons. Like, do you want to take up the file size, or do you want a better recording, or was it for? Just think about what specific application you're using it. Is your number one priority file size? Then probably go with MP3. If your number one priority is quality audio, then go with a larger file size. Like FLAC it's huge, or anywhere in between. And so all that to say, you should be fine with everything, but I would just stay away from MP3s personally and pick pretty much anything else. And so that wraps up our chapter on analog and digital electrical audio. Again, if you have any questions, feel free to comment below. You can also email me. I'll put my email in the description. Again, please like and subscribe, and feel free to share this video with anyone you want. I want this to be a free resource that is very accessible to anybody who needs it. But thanks, and I'll see you in the next video.